Hello, and welcome to the IBM Quantum Industry webinar, Quantum Utility for the Electronics Industry. Today, we're joined by Dr. Rami Ahola and Dr. Charles Chung from IBM. We'll start by hearing from Dr. Rami Ahola, who is the Global Industry Leader for Industrial Manufacturing at IBM Consulting. Rami and his team work with IBM's clients in the electronics, automotive, aerospace, and defense industries globally. Feel free to post your questions in the chat as you go. We'll be selecting and answering them after the talk. Thank you, and over to you, Rami.
Thank you, Jen, and welcome everybody. So my team obviously work across the entire value chain of electronics companies, but a lot of the focus today is going to be on product development. And if you flip them to the next chart, that's where I wanted to give a little bit of a flavor for what's happening, what we see happening in the industry. So if you look at the product today, it's much more than just hardware. It's customer expectations for product are changing. Most customers don't really care about individual product features. What they care about is the experience that they get from the product. Also, customers don't really want to own anything. It's really the outcome that they receive from the product that matters. And where it used to be a value chain approach in the past, it's really now everything lives in an ecosystem. There's not a single company in the world that can go alone. You have to partner with others in your ecosystem to create a product that's compelling to the customers. Now, what that means for product development organizations, there's a bunch of changes that have happened. The value of an electronics product is by and large driven by software and services and the data that those run on, not the hardware. Everything is connected, and you have AI on everything, and that just changes the playing field. Basically, with the product connected, you cannot, as a user, you cannot distinguish what runs on the physical product versus what runs somewhere in the cloud. And last but not least, the fact that your product is connected and upgradable means that product development continues forever, or for as long as you have products out in the field, because the customers will expect that you'll get a new version, you'll get updates to your product, and it will improve over the course of its lifetime. Now, what does this mean for a product development organization? You need to do a lot more than you used to. The physical product is still important. That's still the thing that an electronics customer will buy. But there's so much more. There's cloud services, there's software, there's all kinds of data issues, you name it, but you don't have more budget. At least not a whole lot more budget, which means that the hardware development piece needs to get done with less resources than you used to do it with in years past. So you got to do more with less, effectively. If you flip to the next chart, you don't need to just take our word for it. IBM actually has a think tank called Institute for Business Value that surveys these things. And every 2 years, we do a CEO study that interviews thousands of CEOs across industries around the world. And one of the things that we ask about consistently is, what are your organization's highest priorities over the next 3 years? What you see on the right-hand side is CEOs across all industries. On the left-hand side, you see electronic CEOs. And what's clearly different between the two is that for the electronic CEOs, number one priority by far is really getting new products, new technology, and new services out to the market quickly. And that's where quantum holds great promise to help. And with that, I will turn it over to our main act for today, Charles Chung. Dr. Charles Chung is our quantum industry applications lead for electronics engineering and manufacturing. And what that means in practice is that he helps our clients or companies in those industries identify ways that quantum computers may be able to maybe applied to their most difficult challenges. So with that, over to you, Charles.
Thanks, Rami. So let me start out with a picture. If you've never seen a quantum computer, this is the IBM Quantum System 2. It's a beautiful machine. It's won 8 design awards so far, including the prestigious Red Dot Award. To give you a sense of scale, this machine is about 15 feet high. This center panel here is where the quantum computer is held, and these two panels to the left and right, that's where the control electronics are. Now, to give you a sense of the kind of activity that's happening in the quantum computing world, let me give you a couple of numbers. The World Economic Forum has identified over $40 billion of investment that's been announced worldwide going into quantum computing. IDC is currently measuring the compound annual growth rate of customer spend on quantum computing at almost 50% per year. And the Boston Consulting Group, in a survey of quantum computing users, find that 97% of companies are planning to either increase or maintain their current investment in quantum computing. Of this 97%, 2/3 are planning to increase their investment. These are some pretty impressive numbers. So the question is, why is this happening and why now? And I think there are two primary drivers. One, the business value has been identified, and two, quantum computing has reached utility. And what we mean by that is quantum computers are now able to do useful calculations. Let me start with the business value piece. The potential value to be created is enormous. BCG did a study trying to estimate the value, and their lower end estimate is at $500 billion. McKinsey did a similar study, and their estimate is about $0.6 trillion, so a very similar number. It's because of these opportunities that leaders in the electronic space are working with us in order to build applications for our quantum computers. Now, to give you a sense of the application space, this Venn diagram gives you an overall picture. This white circle is the set of applications that classical computers can solve. This red oval is a set of problems that classical computers cannot solve. And the blue oval here is what quantum computers can do. Quantum computers can, in theory, do everything classical computers can do. Quantum computers can solve some of the classically intractable problems, but not all. Plus, there's this interesting space here where only quantum computers can solve some problems. And so let me go one level of detail deeper. There are 4 main application areas of quantum computers. There are many more, but these are the 4 that are perhaps most well understood. I've listed them in order of feasibility. So we believe machine learning is the nearest term set of applications, followed by chemical and material simulation, then optimization and search, and followed by linear algebra. I'll give you examples of linear algebra, chemical and material simulation, and machine learning in this talk. Let me start with the linear algebra piece. One of the biggest challenges, as Rami was pointing out, in electronics is developing new products. And the way we do this is at a very high level is we typically design a new product, and then we manufacture it, and then we qualify it. And once it passes qualification, we release the product. Now, in this chain, usually for most engineering or electronics companies, the largest computational load is solving large systems of linear equations. And these are very versatile, and we use them for example, in finite element analysis and in circuit simulation and computational fluid dynamics, but they're also quite expensive. Some of these simulations can take days, sometimes weeks, and so they can take a long time. Now, there is a quantum algorithm that can accelerate these simulations. In this chart here, you see the y-axis here is the number of computational steps. You can think of this as the simulation runtime. The x-axis is essentially the size of the simulation. This gray line is the way classical finite element solvers scale, and you can see there's a strong relationship between the size of the simulation and the number of computational steps required. There is a quantum algorithm that has a very different scaling. It's a logarithmic scaling. And you can see that one way to interpret it is that there is a quantum algorithm that can decouple the size of a simulation from its runtime. In other words, in order to do a trillion element simulation is not that much longer than it takes, for example, 1,000 element simulation. So this is an amazing amount of computational power. It's literally an exponential acceleration simulation runtime. Now, let me tell you why we have categorized this as the longest term application area. And that's because, and let me go back and tell you a little bit how quantum computers work. So first of all, we use them in conjunction with classical computers. We believe that quantum and classical are complementary technologies. And typically, there's a calculation that we do with a classical computer, which passes information to a quantum computer, which then passes its results back out to a classical computer. Now, the interfaces between quantum and classical computers are low bandwidth currently. And the input interface is making a lot of progress. For example, the matrices that we use in, for example, finite element tend to be sparse. They also tend to be band diagonal. And we know, for example, how to efficiently load some band diagonal matrices, not generic ones yet, but it's making a lot of progress. We also know in the long run that these matrices are driven by geometry and material properties. Geometry, for example, is highly parameterizable. We could pass those numbers from the classical computer into a quantum computer, and a sufficiently powerful quantum computer could reconstruct the geometry and therefore the matrices, and then perform the computation. Now, the output interface is a little bit more problematic, and the challenge here is that the way the solution vector, and what I mean by that is, for example, in a finite element simulation, it'd be, for example, the stress for every single element in the simulation. The vector of solutions is stored as a superposition of numbers over multiple quantum bits or qubits. When we take a measurement, that superposition collapses, and we essentially are able to output one stress from one finite element. The way you'd brute force overcome this is you'd run this computation over and over again, and then what you'd find, but if you do that, what you'll find is that you essentially eat up all the acceleration that a quantum computer offers. Now, to give you a sense, though, of the kind of innovation that's occurring here, this is a paper that Toyota developed on our quantum computers. Toyota realized that maybe we're asking the wrong question to quantum computers. Maybe we shouldn't be asking what is the stress at every single point in space. Maybe we should be asking a more important question, which is, for example, what is the best design? And in Toyota's paper, what they wanted to do was figure out the structure that had the best thermal conductivity. And the way you do this classically is you identify a candidate structure and calculate its thermal conductivity, and identify a second candidate structure and and calculate its thermal conductivity, and so on and so forth. In Toyota's quantum method, they figured out a way to solve the thermal conductivities of all possible structures simultaneously and then extract the optimal structure. And so you can imagine using this for accelerating product development. You could, for example, simulate many designs and then, for example, extract out the design that had the highest performance or the lowest cost or the lowest power or whatever you're trying to optimize for. So this would transform the role of finite element in product development. We typically don't use finite element for design exploration. We typically use it for design confirmation, and this would be a transformation in its role. But we also see that quantum algorithms will have a greater impact on product development than simply shortening simulation runtimes. And so let me go back to this view. It is a rare product that will go from design to manufacturing to qualification to product release in one step or in one go. Most of the time what happens is that we get to qualification, the new product does not pass qualification, so then we have to go back and redesign it or come up with a change in the manufacturing process and then try again and again and again. And the problem is that this iteration takes months to years, and this is the single biggest contributor to the length of time it takes to develop a new product. What we really want to do is be able to shift leftwards information for manufacturing and qualification into the design step in order to reduce the number of times we have to go through this iteration. So if we think, and the good news is there are a number of quantum algorithms that have been identified to help us with this. So if you go back to example, and let me focus on, for example, stress and vibration testing. So if you go back to Toyota's method, we can think about using a quantum computer or a finite element for virtual qualification testing. Now, this is not something we typically do. It's typically a really hard simulation to do because one, in order to, for example, capture fracture, you have to have a high spatial resolution simulation. It's also a transient simulation, which means that we have to essentially make a movie over time. It's also fracture and buckling and other failure modes are nonlinear. So this is a really difficult simulation to conduct. Adding to the complication is the variation in test conditions. So for example, a common test that we do in qualification is the drop test. Most consumer electronics have to survive a drop. The test is typically a 1 meter drop onto a hard concrete surface. But we know, for example, that you can drop a phone, for example, at many different angles. And some angles it will survive and some angles it won't survive. And to do every single angle is basically not possible today. We also know that even with the exact same test conditions, the exact same simulation, there will be manufacturing variation in the geometry as well as the material properties, and that will result in some manufactured phones passing this test and some not passing the test. And so for all these reasons, we don't tend to use finite element for virtual qualification testing. However, you can think about extending Toyota's method for, first of all, accelerating these difficult simulations, but also doing it over multiple test conditions, multiple manufacturing geometries, multiple material properties, do it all simultaneously, and then extract out, for example, the most robust design. And so this is a way, for example, that we could cut months or maybe even years off the product design timeline. Now, the really big jumps in either cost performance curves in products or even entirely new capabilities really comes from when we introduce new materials. But this is really hard to do. Typically, when we introduce a new product, we either update the design or come up with a new design and keep the manufacturing the same, or we keep the design the same and update the manufacturing, for example, to come up with a cheaper version of the product. We don't tend to do both because that's really hard. When we introduce a new material, we not only introduce a new material, but we have to introduce a new design in order to take advantage of the new material. And we also have to introduce a new manufacturing process in order to work with a new material, which increase the risks at qualification. And so what we really want to do is we want to shift left where it's not only design and manufacturing information, but also material information. And again, there are multiple algorithms to help us with that. Let me first talk about the kinds of opportunities that new materials offers for electronic products. This is a paper that we published with JSR and Mitsubishi modeling light emitters for flat panel displays. We're modeling light emitters that have the potential for 100% internal quantum efficiency. To give you a point of comparison, current light emitters are only 25% efficient. And so this would be an opportunity, for example, of increasing power efficiency of flat panel displays by a factor of 4x. Another area we're looking at is in batteries. This is another paper we published with Mitsubishi Chemical. The challenge with batteries is they don't store that much energy. So for example, gasoline here, you can see has enormous energy density compared with batteries that have, a fraction of its energy density. However, there is a battery that has a theoretical energy density approaching that of gasoline, and that's a lithium air. And so what we do with Mitsubishi Chemical is we model one of the reactions that occurs, for example, in a lithium air battery. Now, in the area of material qualification, one of the common tests that are required at qualification is survival of exposure to humidity. And so we worked with an aerospace manufacturer to, for example, model the reaction of magnesium to humidity. Magnesium is interesting because it is the lightest structural material, but it has challenges in that it is readily corroded by water. And so we modeled the interaction of solid magnesium with gas phase water in the hopes of understanding this reaction in more detail so that we could find a way to slow down or even completely suppress this reaction. Let me turn now to machine learning. This is the nearest, this is the application area that has the nearest term feasibility. What we're seeing with quantum AI is that we're seeing that in some data sets, not all data sets, but on some data sets, quantum AIs can achieve higher accuracy, sometimes with less data. And you can imagine using this in the electronics industry, for example, for optical quality inspection. But you can also imagine using it for those manufacturers that build imaging equipment, particularly medical imaging equipment, such as MRIs and CAT scanners and endoscopes, for incorporating an AI that can help with image classification. And so one of the challenges with medical image classification today is there are a lot of errors. And so there is an AI right now that is a certified medical device. It gets about a 79% image classification accuracy rate, which is pretty good. It's only a little bit lower than humans' accuracy rate, which is about 82%. Now, we know that the estimated number of radiology errors made every year is on the order of 40 million. This AI that's being used right now, it has a false positive rate of about 25%. Now, false positives are terrible for the patient. If it was cancer, for example, that would mean that it's saying that a patient has cancer when the patient really doesn't have cancer. Um, a false negative rate is about 16%, and a false negative is probably even worse for the patient. That would be saying that the patient does not have cancer when the patient actually does have cancer. And so while the accuracy is good for AI, it's still an 80% accuracy rate implies a 20% inaccuracy rate. And we know that medical liability costs are about $55 billion per year. And of that 55 billion, radiology errors compose the second largest category of errors. We also know that in classical AI, it's hitting limits in these well-developed use cases such as image classification. This is a paper put out by MIT, and they looked at trends in accuracy. And so, for example, they looked at ImageNet. This is a good example because there's an annual contest. They just looked at, for example, the winner of 2022 and 2021 and 2020 and so on and so forth, and they just looked at the trend. And what they saw is in 2022, when the paper came out, the best uh, model had an error rate of about 9%, and that cost $1 million to develop. Just extrapolating trends to achieve an error rate of 5% would cost $1 billion. And to get down to 1% error rate would cost 10 to the 16 $16. That is $10,000 trillion. And oh, by the way, you will also emit 1,000 times more carbon dioxide the entire world emitted last year. So in order to substantially increase medical image classification category accuracy, something has to change, probably, and something has to change that will improve things by orders of magnitude. An interesting place to look is in quantum AI. This is a paper all put out by the European Space Agency and MIT. What they're looking at is satellite imaging, and they wanted to classify which images had an erupting volcano, such as these four, or did not have an erupting volcano, such as these five. Now, they came up with a hybrid quantum classical neural net, and there are a couple of layers of classical neural nets, and then coupled with a couple of quantum neural net layers, finally a final classical neural net layer. The current state of the art, the best classical AI on this particular data set is a 2 million parameter AI that achieved an 85% accuracy rate, and that is precision, recall, F1 score, and accuracy. Their proposed hybrid quantum classical model achieved a precision recall F1 score and accuracy rate of 96%. That is an 11% increase. And as we saw in the previous study, accuracy is around 95% is worth about $1 billion. And so this is the kind of value that we're identifying with quantum computers. We're seeing AIs that can achieve $1 billion worth of accuracy, batteries that are order magnitude or 2 greater in energy density, ways to cut the product development timeline by months or years. Now, let me give you a sense of where the technology is right now with quantum computing. As I said, it's reached utility. We can do useful computations now. Let me start with a common question that we get, which is how does quantum compare to classical, particularly classical AI? And we at IBM, we do not see these technologies as competitive technologies. We see this as complementary technologies. All three forms of compute are good at different things, and therefore they work well together. And in order to tackle our most difficult challenges, we're going to have to use all three. Now, the current status with quantum computers is last year we executed a computation that went beyond what classical computers can do. This is so important that it made the cover of Nature magazine, and this blurb here maybe summarizes it best. Error mitigation empowers quantum processors to probe physics that classical methods cannot reach. So we reached this crossover point where quantum computers can do things that classical computers cannot do last year. Going forward, we call this era the era of quantum utility, where quantum computers can now perform useful computations. Looking forward, this is our roadmap. There's a lot of information here, so let me orient you a little bit. There are 3 layers here. The bottom layer you can think of as the hardware, the middle layer you can think of as the software, and the top layer you can think of as the applications. Where we work with most companies is developing applications for quantum computers because that is where the value is for them. We're here in 2024. We have the Heron processor up and running. There are 2 trends you should pay attention to in the hardware. One is the qubit count. It's increasing. For example, we have 133 qubits today. We expect a 1,000 qubit machine next year. The other trend is the number of operations we can perform on those qubits. We can do 5,000 operations today. We expect that number to triple by 2028 to 15,000 operations. And in 2029, we expect a little quantum leap in performance where we can execute 100 million operations. That is where we'll have the first error-corrected quantum computer. We do expect the application space to suddenly expand with the arrival of error correction, but we expect the first applications to actually emerge before 2029, likely in quantum machine learning. Let me also inform the technology strategists out there about a discussion going on in the quantum computing community. And the question is whether a fast follower strategy will work with quantum computing. And the current consensus is no. And the argument goes something like this. Once the first killer applications are executable on quantum computers, we expect that the demand for quantum computers will suddenly increase. However, we do not expect the supply of quantum computers to suddenly increase because they're big, expensive machines that take time to get up and running. And so there will be this supply-demand mismatch. If you don't already have access to quantum computers at that time, you're unlikely to be able to gain it. Without access, you're not going to be able to attract talent, and without access and talent, you're not going to be able to innovate in this space, maybe for years. So I've given you a lot of information. Let me summarize it with a couple of recommended actions. The first is realize that quantum computing has high potential for disruption. At least establish a strategic plan around this technology. That means 2, identify your quantum opportunities and threats. And 3, build in-house expertise so you can make informed decisions about this technology. The last is start today. You saw that quantum utility is here today. You also saw that industry leaders in the electronic space are building advanced quantum capabilities now. The learning curve is steep. Most companies take most companies working with us take 2 years to master the technology, and then another 2 years to convert that mastery into applications. And lastly, you should know that intellectual property is being secured now. So with that, let me take some questions. Let me point out we have 2 links here. The first is if you'd like to start using our quantum computers, you can create a free account today. Access is free, and you can start digging in using our quantum computers right now. The other is if you'd like to learn more about quantum computing use cases in the electronics industry, you can follow this second link. Okay, thank you very much.
Thank you so much, Charles. We do have quite a number of great questions here. So,
Great.
first up is how should automotive OEMs approach quantum in crawl, walk, run phases?
Good question. So first of all, let me say that the automotive industry is already quite active in quantum computing. And let me say that I think the advice I would give here is very similar to what I give for most companies, which is the steps that I told you back here, which is a lot of companies have a lot of trouble just understanding how a quantum computer can be useful to them. So identify your quantum opportunities. That is a skill that needs to be developed all on its own. The second is build in-house expertise. And in particular, the specific skill that we would recommend here is uh, start using our quantum computers, figure out how to write code for them. And what we do at IBM, we work with clients on both these things. We have a program called the Quantum Accelerator. We'll work with you on and help you build the capability of identifying quantum opportunities and threats. And then we take one of those and we convert that into a proof of concept. And so in other words, we build the code to run that use case on our quantum computers and as well as the workflow to use that code. And then once you have this business skill of identifying your quantum opportunities and this technical skill of knowing how to use a quantum computer for those opportunities, I think those would be the 2 most important steps in order to start figuring out how to incorporate quantum computing into your corporate strategy.
Perfect. I think you kind of touched on this a little bit, but I'm going to go ahead and read this question and maybe you can provide some more nuance. So since we were discussing about different industry verticals and domains like machine learning, optimization, etc., my question is, as of now, in current scenarios with current hardware, which domain looks promising, or is which domain is most quickly approaching quantum advantage? Like, the domains mean specifically like quantum machine learning or optimization. I think you already touched on this, but just to explicitly answer this question.
Sure. So the nearest term application area is we believe to be machine learning. As you saw in this paper from MIT and the European Space Agency, we're seeing increases in accuracy. Let me go back to this. We're seeing increases in accuracy on some data sets, not all data sets. We're also seeing on some data sets, you need less data in order to achieve, for example, a similar level of accuracy as classical machine learning. So where we're focusing is machine learning use cases where accuracy is important, or accuracy has reached a ceiling in classical machine learning, and or where data is hard to get. And a good example is anomaly detection. Anomaly detection is an area where data is, anomalies are by nature rare, so data is hard to get. And oftentimes what we're seeing with current classical approaches to anomaly detection is that the false positive rate is overly high. And probably the false negative rate is also overly high, but that tends to be hard to measure. So, but given that, looking at our current timeline, I think in terms of what applications are most promising, I would say depends on your timeline. It also depends on what where your common opportunities are. I mean, I think a lot of people probably have opportunities here in machine learning, where we believe the first applications will appear in the next 3 plus minus 1 years. But error correction is going to expand the application space. We do expect that certain use cases in the other areas of quantum application areas like optimization, chemical and material simulation, linear algebra will open up in 2029. The feasibility of those use cases is very strongly use case specific. And so, I would suggest if you'd like to have a discussion with us, we have a survey, a quick 3-minute survey coming up after this, and there'll be a link in there where you can contact us for further discussion. And maybe I'll put that link up right now.
Cool. So thank you, Charles.
Yep.
We'll jump in. We'll take maybe 2 more questions.
Yep.
So there's one here, about image classification. I believe that you've already answered that one, so I'm going to go to the next one here. Let's see. So we have, what are some specific quantum use cases that have been done with some of our electronics clients, if we're okay to share?
Sure. So Sony, I believe, is using our quantum computers for image classification. GSR is you saw the use case of increasing power efficiency in displays, as well as increasing battery density, energy density with Mitsubishi Chemical. We're also have published a paper on modeling, for example, photoresist for the semiconductor industry. Bosch, for example, is using our quantum computers to explore new materials in the electronic space. I believe we just published a paper with them on modeling metal oxides. Let's see, what else comes to mind? There are quite a few papers that we've published in this area, and so those are the ones that immediately come to mind. One place that you can take a look is in this paper, this white paper that we published for use cases in electronics, that will give you a couple of more applications to think about in the electronic space.
Cool. And maybe for the last question, I'll actually turn it over to Jennifer. And that is, for all of this information that has been shared today, how do people get access?
How do people get access? So we have 4 levels of access to our quantum computers. So the first one is we have free access. We make all of our quantum computers, all of our quantum computers, they have at least 100 qubits. And so you have access to our most powerful and latest quantum computers through our free access. You just have to go to this link, create an account, and you can start programming on our quantum computers today. The second and third level are paid access. The second level would be sort of a per minute access. The third level would be buying a chunk of time on our quantum computers. They're very similar to like the way mainframes work. It's cheaper to buy a chunk of time than it is to buy it per minute. And then the last level is a dedicated system. If your organization has gotten to the point where you can use up all the bandwidth on a quantum computer, then talk to us about the possibility of reserving a dedicated system for your organization solely.
Cool. And Jennifer, specifically for like the studies that were in this presentation and some of the information that was in this presentation, how can people get access to that
Yes,
after
thank
this?
you, Ethan. You could scan the QR code on the previous slide. I did drop the link to the IBV study in the chat for those interested in further exploring quantum computing use cases for the electronics industry. And then today we are asking if you have a couple of minutes. It should only take no more than 3 minutes to spend some time giving us feedback on this industry webinar. You can scan the QR code there, and I will also drop the link in the chat so that we can make sure that the content is useful for you. And also, if you have ideas for future topics, we welcome your suggestions. So please take a couple minutes now. We'll leave the webinar open so you have access to the QR code for another 2 minutes. And thank you so much for joining us today for this talk. Thank you, Charles. Thank you, Rami, for sharing your expertise with us.
Thank you, everyone. And I believe in the survey, if you have questions or would like to contact us, there's a way to contact us through the survey. So.
We'll be following up with email, the link to the playback. So those who aren't able to join today or who want to peek back at the slides and the talk, we'll follow up with the recording. And it will include additional information about reaching out to us if you're interested in learning more about how to get started working on our quantum computers.